All right, we're back here, Physics 1151. We're going to finish up our first set of notes on Chapter 22, which is charges and electricity, and then we're going to get into the second part, which is Coulomb's law. So we ended the other day with the methods for charging an object. We discussed charging by rubbing and charging by contact. We first started with the origin of electricity, which lies at the molecular, the atomic level with charge, right? Atoms are composed of electrons and protons. Protons are positively charged, electrons are negatively charged, right? And these charges create electrical forces and electrical effects that we're going to be studying in the next few chapters. Then we discussed a little bit on conductors and insulators. We discussed. Remember, conductors are materials that electrons can flow freely through. Insulators are materials in which the electrons are tightly bound to their native atoms, in which they are not able to move and conduct electricity. Then we got into the first two methods for transferring charge. Okay, for an insulator, you can charge an object by rubbing two objects together. For example, here's fur or your hair, and here is a rod. And if you rub them together, you will transfer electrons from the fur to the rod, and the fur becomes positively charged and the rod becomes negatively charged. So which one will become positive and which one becomes negatively charged depends on their electron affinity. And remember, if you're up closest to the upper left here, these materials tend to lose electrons easily or give them up and become positively charged. Okay, human hands, fur, hair, okay, so our skin. And so most of the time we become positively charged. We give up electrons, right? And these materials, these hard plastics and vinyls and Teflons and silicon over here, these materials become negatively charged, right? They're at the bottom right of the table. So for example, if I rub my head with a Teflon rod, the Teflon will become negatively charged and the hair on my head will become positively charged. So I'm transferring electrons from my hair to the Teflon. And conservation of charge says we can't create or destroy charge, we can only transfer it. So this table is a good little table for determining when you rub two objects together which one will likely become negatively charged and which one will become positively charged. Okay, so when we rub two objects together, one object becomes positively charged, one becomes negative. And that's, for example, when you slide down a slide at a park, you become positively charged and the slide becomes negatively charged. Then we discussed for metals, a common method for charging is to charge by contact. And so if you bring a rod, for example, that's been negatively charged, and we put it close to a metal and then we touch it. This phenomena makes use of the fact that the electrons in the metal, remember metal's a conductor, and so the electrons are free to move. And if I put some negative charge on here, these electrons are going to repel each other, right? They're going to want to spread out as far as they can to minimize the repulsion. And so I spread negative charge uniformly over the surface of a metal. So this makes use of the fact that the electrons in a metal are free to move. You can do the same with positive charge. I can take a positively charged rod and touch the metal, and it'll become positively charged. Now, a more useful application of this was when one conductor touches another, and the first one has been charged. For example, if we charge the positive metal and then a conductor, like you, touches the metal, right? The metals are these charge is going to be shared equally between the two conductors, or it's going to spread out uniformly. I shouldn't say equally, but it will spread out uniformly onto the two conductors. And last but not least, if this charge is free to travel to ground, for example, if I'm in contact with the ground and not separated by an insulator, that becomes the third conductor, and so the charge can be transferred to my body and then to ground, and that's a very bad thing, right? That constitutes a current going through your body, which often can kill you or shock you. So when metals are in contact with one another and one of them has a charge, that charge will diffuse onto all three, or all of the metal or conducting surfaces. That application we discussed was grounding with a lightning rod, or with we talked about the three-prong plugs. The final method of charging, which can be used to charge neutral or temporarily charge a neutral object, is called charging by induction or by polarization. So let's look at a concrete example here. Suppose you have a rod and you charge the rod positively. So the rod has a positive charge, and we bring it near the metal, but we're not going to touch the metal. Okay, the metal is neutral, okay, because we haven't put any charge on it. But what's going to happen here? Well, remember, the electrons in a metal are free to move, right? And so they're going to be attracted by this positive charge, and so the negative charge is going to shift toward this positively charged rod. But it can't jump the air gap, right, unless this electric field is big enough, which we're not going to consider right now. So the negative charge gets attracted by the positive charge on the rod, and the positive charge will move away, right? The positive charge gets repelled. So as we sit and we hold this rod right next to the metal, we temporarily separate the charge. The positive charge is repelled, the negative charge is attracted. And the charge tends to shift by just a little bit, right? It can't shift too much because this positive charge will also attract the negative charge. And so you get an equilibrium condition in which the negative charge has shifted slightly toward the positively charged rod. And as long as we hold this rod close to the metal, we will induce a separation of charge, okay? And then as soon as what's going to happen is when we remove the rod, so now we move the rod back away from the metal, well, then the negative and the positive charge will attract one another, and the metal will return to its initial uncharged state. So when you bring a charged object close to a metal, you temporarily induce a separation of charge, and that's called charging by induction. So try this experiment at home. Take a comb and run the comb through your hair. Okay? And so the comb is going to, remember, your hair is going to give up electrons. And so your hair, well, actually you couldn't do it with your hair. Let's pick a better example here. So let's take, you'd have to take a glass rod, if you want to charge it positively, and rub it with silk cloth, okay? The glass rod will give up charge and become positively charged. The silk will become negatively charged, okay? So that's acquiring a positive charge. And then we can bring it near any neutral object, okay? And you're going to get the same effect, okay? You're going to induce what's called a dipole moment. You're going to separate the charge in the material, because the positive charge is going to want to move away, the negative electrons are going to want to move toward, and so you're going to separate the charge in this material. And what's going to happen here is, if you look at the picture, the negative charge, this negative charge on the near part of the material is closer to the rod, and that's going to be more strongly attracted to the rod, then the positive charge is repelled because that's further away. And so you're going to experience a net attractive force toward the rod. And you can do the same thing if paper, you can take little snips of paper, and you can take a comb, and if you run the comb through your hair, the comb will be charged negatively. You put that negative comb near the snips of paper, and it's going to attract the paper because the positive charges on the paper will be closest to the negative charges, and they'll be more strongly attracted than the negative is repelled. Okay. Now, the minute that you move the comb away, this separation of charge, the charges go back together, and their material becomes, the separation of charge goes to zero. I'm sorry. So this is called charging by induction. So numerous molecules in nature have a separation of charge naturally, and one example of prominent importance is water. So water has two hydrogens and an oxygen. And recall that the hydrogens are going to want to give up their electrons so that they have a full, or in this case, an empty shell, and the oxygens are going to want to have a full valence shell, and so they're going to want negative charges. And so you get this separation of positive and negative charge where there's more positive charge near this hydrogen atom and there's more negative charge near the oxygen atom, and that creates a temporarily separation of charge called an electric dipole. And so these polar molecules like sodium chloride, table salt, or water, or ozone, these molecules naturally have a separation of charge called a dipole moment. You can even induce dipole moments in nonpolar substances, for example, oils or grease, if we apply an electric field to them, which temporarily separates the charge. So these dipoles exist naturally in nature through polar solvents, polar molecules, and they can also be temporarily induced if we apply an electric field to the material, in this case due to the charged rod. So let's do an example here.
This is a plastic cup that has a hole drilled into the bottom of it. So when I fill it with water, it leaks out of the bottom.
If I charge the pipe and then bring it close to the stream of water, the water is attracted to it. That's because water molecules are polar molecules.
Water molecules look a little bit like Mickey Mouse. The two hydrogen atoms are bunched up on one side of the oxygen atom. And while the molecule itself is neutral overall, it has a positive end and a negative end because of the way it's shaped. Molecules like water that have an asymmetrical distribution of charge are called polar molecules.
Let's say the pipe has a negative electrical charge. If I bring it close to the stream of water, the water molecule flips so that the positive end is pointed towards the negatively charged pipe. Opposite charges attract, so the water is drawn towards the pipe.
This is an experiment you can do for yourself at home fairly easily. All you need to do is turn on the faucet so a little bit of water comes out, and then you place a charged object near the water. Any object that'll hold a charge will do, like a comb.
Or a balloon that you've rubbed on your head.
Or a plastic pen.
Thanks for watching. I hope you'll join us again soon for another experiment.
This will be kind of a mess.
Okay, so that the water flow example, the deflection of water, was one example of charging by induction. Once again, I apologize for not being able to do the demo. I did it with out of my sink and I couldn't get a nice laminar flow without turning the flow rate up enough that it was difficult to observe much reflection. So taking it out of a cup like what they did in the experiment is an easier way to observing that. But the gist of it is that when you put a charged object near a neutral object, you will always get an attraction, right? Because it'll always pull one end of the it polarizes the material, in this case the molecules. And so in this case the negatively charged rod would attract the positively charged side of the molecule, and there's going to be a stronger attraction between the positively charged molecule and the comb than there is a repulsion between the negative part of the molecule and the comb, because the negative part is further away. And so you tend to get a net attraction. And so that's an example of charging by induction. And so you can take some snips of paper and a comb, or take a stream of water going out of a cup like that, and you can observe that effect pretty easily. It's a little tougher out of the faucet, at least out of my faucet it was, to observe. I could observe the effect, but it wasn't easy to see on the camera. So you can do that. So the last example is charging by contact and by induction. Okay, so let's suppose that we take our positively charged rod and we bring it close to the metal sphere. Remember, so we're not touching yet. We're not going to touch yet. So we take the negatively charged electrons are going to be attracted toward the rod, leaving behind the positive charge. And so you tend to induce this separation of charge. Okay, now we're going to connect a grounding wire, a wire to ground. So we're going to connect a wire to the sphere to ground. Okay? And what's going to happen now is that there's a path for electrons to flow freely between the wire, which is a conductor, and the sphere. So electrons are going to come up from ground, and they're going to neutralize some of this charge. Or you can think of it, it's not really happening, but you can think of it as the positive charge running away from ground, repelled by the positively charged rod. It's really the electrons coming upward, but you can think of it the same way. It's the same effect. And so what happens here is when we finally, now we're going to remove the grounding rod after this happens. So some of this has been neutralized here. We've got a net negative charge. We take away the grounding rod, and now even after we remove the rod here, this negative charge can't go anywhere. It can't go to ground. And so it's going to be spread out over the sphere. And so the net effect of all of this, by all of this I mean connecting a grounding wire after you bring the rod close, and then removing the ground wire and moving the rod away again, is that you put a charge on the metal which is opposite of this sign of the charge induced. So in other words, if this were a negatively charged rod, we would induce positive charge onto the sphere after removing the grounding plate, or the grounding wire, I'm sorry. And so this is an example of charging by contact and by induction. It's a method for producing charge onto a metal sphere. So let's finish up this set of notes here with an example conceptual exercise. So suppose that you have a rod made from an insulating material, or could be a comb. Okay? And suppose that it has a net charge. And it doesn't matter right now whether it's positive or negative. It's just charged to one polarity. And the copper sphere is neutral. And suppose we hold the rod or the comb close to the sphere but not touch it. But don't touch it. Which of the following statement is true? In other words, will there be an attractive force between the sphere and the rod or the comb? Will there be a repulsive force? Or will it depend on the sign of the charge on the rod? Okay, so take a minute, pause your video, and think about it. Okay, and then turn your video on. And so the answer is it doesn't matter what sign of charge we put on this rod, the sphere will always experience an attractive force toward the rod. Okay, and that's just due to induction, right? We're going to induce a separation of charge. So here's a positively charged rod. The negative charge is going to be attracted. Positive charge is going to be repelled. But the negative charge is closer to the rod than the positive charge. And so the attractive force between the near side of the paper or whatever the material is and the rod is stronger than the repulsive force, and you get a net attractive force. And so again, if we bring a charged object close to an insulating material, or even a metal, as long as it's close, we will always induce an attractive force, as long as this is close to the surface here. And so that concludes this first set of notes. Okay, so now that we've discussed qualitatively the origin of electricity, some methods for charging objects, the difference between conductors and insulators, the next thing we want to do is we're going to start to develop the mathematical machinery to calculate the magnitudes of these attractive and repulsive forces between charges. This will lead into several applications, and then we're going to get into, after we do electrostatics, we're going to get into electricity, voltage, current, and at the end, electromagnetic radiation. So we're going to start with what's called Coulomb's law, and that's used to calculate the force between charges. Okay, so we know that if you take two charges, a positive and a negatively charged, for example, a proton and an electron, and we know that they're going to be attracted to one another, right? And so they're going to exert equal and opposite forces on one another. Newton's third law, the forces of action, reaction forces in pairs, right? So if they're the opposite sign, the positive charge will be attracted toward the electron, negative charge. The negative charge will be attracted toward the positive charge, and so the forces will be pointing toward one another. Okay, the force of attraction. If you have two charges that have the same sign, for example, two positive charges, they're going to be repelled, right? And so charge 1 is going to be repelled by charge 2, so the force points away from the charge 2. The force on charge 2 due to 1 will point away from 1, and so if they're the same sign, the forces will point in opposite directions. They're repelled. And so we know the directions of the forces. If you have opposites attract, like charges repel, and so always the force between two charges will act along the line between the two charges. Okay, attraction meaning toward one another, repulsion meaning away, but the force will always lie along this line connecting the two charges, or the two charged objects. Okay, if we know the magnitude of each charge, Q1 and Q2, if we know the net charge on each body, and if we know how far they're separated by, Coulomb's law is the equation that is used to calculate the magnitude of this attractive or this repulsion force exerted on the charges, by the charges on one another. And it's a pretty simple equation. It says that the force depends only on the net charge of body 1, Q1, multiplied by the net charge of body 2, so the product of the two net charges, divided by the square of the distance between the charges. And then you've got this constant here, K, which right now, let's not worry too much about it. It's a constant, okay? And there's another way we can express K. It's 1 over 4 pi times this permittivity of free space, but either way, it's a constant, and it's the same magnitude. K is equal to 1 over 4 pi epsilon naught times the product of the charges over r squared. And so this is the magnitude of the force, and the direction is given by whether they're attracted or repelled. Okay, so when we're using this equation, for simplicity, we're going to always just include the magnitudes of Q1 and Q2, no signs. Okay, the signs will be dictated based on whether it's an attractive force, in which case the sign of the force will point toward the other charge, or if it's a repulsion force, in which case the force will be pointed up away from the other charge. And so this is the magnitude of the force, is the product of the charges over r squared times this constant, which is K is equal to 1 over 4 pi epsilon naught. Okay? So if this is a proton and a neutron, for example, the proton has a charge E, which is 1.6 times 10 to the negative 19 coulombs. The electron has a charge negative E, but in this equation, we would just use the magnitude of each charge as Q1 and Q2, noting that the direction would be dictated by the fact that they're attracted. The force would be pointing toward one another. The author uses the magnitude bars. He's got bars over the Q1 and the Q2. And we can do that too, but just for brevity, I'm omitting it, as long as we remember that we will only include the magnitudes and not the sign here, so that F is always a positive value. And again, we'll use whether it's attraction or repulsion to dictate the direction. Okay? So again, like charges repel, opposites attract. Force is always along the line between the two bodies. Okay, to illustrate the effect of the size, of the amount of charge and the separation on the strength of the force, let's do a ratio problem. Okay, so suppose that we have two charges, Q1 and Q2, and they're separated by some distance r. So Q1, Q2. Now we're going to double the distance between the charges, so r we're going to double to 2r. We're going to separate them by twice as far. And what we want to know is by how much, by what factor is the force going to change? Okay? So we already know that since r is in the denominator, a bigger separation means the force is going to get smaller, right? So if we increase the separation, we know that the magnitude of the force will decrease. So what we want to do is determine by how much. Okay, so for ratio problems, remember, first step we always need to do is we need to find the mathematical equation relating the distance between charges to the force. Okay, and so that's Coulomb's law, right? Coulomb's law relates the magnitude of the force to the separation between the charges. And it doesn't matter whether we use this version with the K as the constant or this version with 1 over 4 pi epsilon naught. It's the same number regardless. So let's just use the latter. Okay, so we're going to write this equation twice. We're going to write it once for the initial condition, in which the separation is r, and we're going to write it once for the final condition, in which the separation is r prime. Okay, and I'm going to denote, since the force is going to be different when we change the separation, it's going to be some different value, I'm going to label this force magnitude by f prime, just to denote it's different. And I could put in 2r right here instead of r prime, but let's just generalize it right now by keeping it in terms of r prime. So we write the equation twice, once for the initial separation and once for the final separation. Then we're going to take the ratio, since we're trying to do the ratio of f prime over f. We've got this equation for f prime in the numerator, and we have the equation for f in the denominator. Okay? Now everything's going to cancel out. All these constants cancel out. The charges Q1 and Q2 are the same under both conditions. We haven't changed them. The only thing we've changed is the separation, R to R prime. So everything else is going to cancel out, and we're left at the magnitude, F prime over F, is just R over R prime squared. Okay. Now we can substitute R prime as 2R, and we see that the force is only 1/4 of the magnitude as it was previously. So what this says here is if we take two charges and we double the distance between them, the force does not drop to 1/2, but rather it drops to 1/4 of what it originally was. And that's because you have R squared in the denominator. So if I make R into 2R and I square it, the force is only 1/4. Okay? And again, you don't have to go through all these steps. You could have just substituted 2R in right away, but I did it here because now I can generalize this result. So for example, if R prime is 3R, then substituting 3R in, the force becomes 1/9 of what it was. And if R goes to 4R, it drops to 1/16. Okay? So every time I double the distance between two charges, the force becomes 1/4 of what it was originally. Now there's a little bit of an assumption here. It's not a big deal now, but it will become a little more important later. When we derive Coulomb's law in this simple equation here, this only applies strictly if the size of the charges is much smaller than the separation. The charge bodies is much less than the separation R between them. In other words, these charge bodies are relatively small compared to their separation. Otherwise, you have to use integral calculus. You get a similar equation, but you have to integrate, and it becomes a little more complicated. So right now, we're assuming that the size of these charged bodies is much smaller than the separation between them. Okay. So now what about instead of doubling the distance, what happens if we keep the distance the same, but we stick twice as much charge on each body? So instead of a charge being 2Q1 and Q2, let's make this 2Q1 by doubling the charge, and let's make this 2Q2 by doubling the charge on this body. So what's going to happen to the force here? Okay. So we're going to do the same ratio problem. Okay. We're going to write the equation a second time. Only here we're going to have a new value of Q1, and we're going to have a new value of Q2. So I'm denoting these by primes, and the result will probably be a different magnitude of the force. So we're going to denote that by F prime. Okay. R is going to be the same. That's a typo, so we need to leave R alone. And so when we take the ratio, if R prime is equal to R, these R squares cancel, all the constants cancel, and we're left with just the ratios of the charges. And now if we put Q1 goes to 2Q1 and Q2 goes to 2Q2, we see that if we double the magnitude of each charge, the force will be 4 times greater than it was originally. So putting more charge on the bodies increases the force. And so you should be able to do these ratio types of problems using Coulomb's law. And you don't have to, I overdid it with the steps a little bit, primarily just to show you how to do it. You could have, in this case, just put 2R in. And for the second example, we could have just put 2Q1, 2Q2, and you would have seen that it's 4 times greater, but I was a little more methodical here to show how it's done. So you should be able to do that. Here's another example, and it's called a class exercise because I'm going to give you the answer, but you can calculate this on your own, and you should as test preparation. So let's consider a hydrogen atom. And the hydrogen atom is just a single electron orbiting a proton. And the average distance between the electron and the proton is about 0.53 angstroms, which is about 0.53 times 10 to the negative 10 meters. So in the first part of the problem, we're going to use Coulomb's law, and we're going to calculate the magnitude of the force between the proton and the electron. Okay? And we know that the magnitude of each charge is 1.6 times 10 to the negative 19 coulombs. And we know that the separation, r, is 0.53 times 10 to the negative 10 meters. And so when you plug that in, and you should do this, you find that the force is 8.2 times 10 to the negative 8 newtons. That's the magnitude. The force is attracted. They're pointing toward one another because the proton and the neutron are attracted, or the proton and the electron are attracted. Okay. Now that we know the magnitude of the force, in part B, you can calculate the speed of the electron as it orbits the nucleus. Okay. And remember, as the electron orbits, it orbits in a circular orbit. And so it experiences a centripetal acceleration. Remember, F is equal to mv squared over r. And so if we plug in our Coulomb force F, and we plug in the mass of the electron, which is 9.1 times 10 to the negative 31 kilograms, and if we plug in r as the distance, we can get that the speed of the electron, at least classically, is about 2.18 times 10 to the 6 meters per second. Okay. Now, suppose we want to compare this electrostatic force between the proton and the electron with the gravitational force. And so the gravitational force is given by Newton's law of gravitation, which you did in first semester, and you can look that up. It's equal to G, big G, Newton's gravitational constant, times the mass of the proton, or the mass of the proton times the mass of the electron divided by r squared. And you can calculate that the magnitude of the gravitational force, it's attractive, is 3.59 times 10 to the negative 47 newtons. Okay. Now, if you compare these forces, the force of gravity between the proton and the electron, with the Coulomb force, 10 to the negative 47, 10 to the negative 8, the electrostatic force is 10 to the 39 times stronger than the gravitational force. Okay? And the point of this whole example, is that the gravitational force between protons and electrons is so small compared to the electrostatic force that we usually can neglect. We can neglect it. And that's why when you're taking your chemistry classes, you really don't need to talk too much about the gravitational force when you're dealing with atoms and molecules, because it's so small, because their masses are small, that we can neglect it compared to the electrostatic force. So you should work through this class exercise. What happens here if we have a charge Q sitting here at the origin, and we have three charges, Q plus Q here, a plus Q here, and a plus Q here. And we want to determine the total force on this charge. Well, how do we do it? Okay. The answer is what's called superposition. And in other words, we can use Coulomb's law to calculate the force of each of these charges on the charge in the center individually. We calculate the magnitude, and we calculate the direction by whether it's attractive or repulsion, and we get a vector of a given magnitude and direction. So that's the force, for example, here, of the charge in the center due to the charge on the top. And then we calculate it due to each of these charges individually, and then we add up all three vectors to get the total vector using vector addition, and we get the total force. And so in other words, if we have a whole bunch of charges, Q1, Q2, and Q3, and we want to determine the total force on some other charge, all we need to do is apply Coulomb's law separately for each charge and add up all the forces to get the total force. And this is what's called superposition. And I think the easiest way to illustrate is to show this is just by doing an example. So let's do that. So we have three charges here, Q1, Q2, and Q3. And Q1 has a magnitude of plus 6 microcoulombs. Micro is 10 to the negative 6 coulombs. Q2 has a charge of negative 8 microcoulombs, and Q3 has a charge of 10 microcoulombs. And what we want to do is determine the magnitude and the direction of the force exerted on Q3 by Q1 and Q2. Okay, so we're going to apply Coulomb's law, which is right back here. We're going to apply Coulomb's law separately for each pair of forces to get the magnitude, and we're going to get the direction by whether they're attracted or repelled. Okay, so let's start. So the first step that we're going to do is we're going to draw our free body diagram, just like you've done throughout mechanics. So we're going to sketch the forces acting on Q3. So let's look at Q1. Q1 and Q3 are going to be repelled. They're both positive. The force is along the line between them, but it's going to be repulsion. So it's going to point to the right. And so I can draw this as an arrow, and I'm going to write it as F31, the force on 3 due to charge 1. And it's pointing, let's call this the positive x direction, and let's call up the positive y direction. So this force would be along the positive x direction. Then let's look at the force on 3 due to 2. Okay, 2 is negatively charged, 3 is positively charged, so they're going to be attracted. And so the force acting on 3 due to charge 2 is going to be pointing straight down toward charge 2. And so we can draw that as a vector and call that F32. So now we know the directions of each of these forces, and we're going to add them up. We're going to add the two vectors to get the total force. But first we need to get the magnitudes of each of these forces, F31 and F32. We know the directions. We don't know the magnitudes yet. So let's use Coulomb's law here. So we've drawn our free body diagram. We've assigned a coordinate system. We've drawn the vectors. Now we need to get the magnitude of each vector. So we use Coulomb's law. And so we can plug in the magnitude of charge 1, which is 6 times 10 to the negative 6 coulombs. And we can plug in the magnitude of charge 3, which is 10 times 10 to the negative 6 coulombs. And we're going to use K as our constant. It really doesn't matter if we use K or 1 over 4 pi epsilon naught. And they're separated by 0.3 meters. And so we're going to square that. And when we plug all these in, we get a magnitude of 6.0 newtons. Okay, so let's put that on our diagram. F31 is 6 newtons, and it's in the positive x direction. And we can do the same for the force on 3 due to charge 2. This should be Q2 here, sorry, typo. So it's K times Q2, and Q2 is 8 microcoulombs, or 8 times 10 to the negative 6 coulombs. Q3 is 10 times 10 to the negative 6 coulombs. And they're separated by 0.2 meters, and we square it. And we find the magnitude of force of 3 due to 2 is 18 newtons. So we go back to our diagram. F32 is 18 newtons, and it's pointing along the negative y direction. F31 is 6 newtons, and it's pointing in the positive x direction. So now we know the magnitude and the direction of each of these forces, and now we just need to add the two vectors to get the total vector, which is the net force acting on charge 3. So now we need to do vector addition. And I have a tutorial, a little review of vector addition as an appendix. If you've forgotten some of this, go back to the review and then come back. That's at the end of this set of notes. So we can write the force in component forms. In other words, we can get the total x component, which is the x component of F31, which is 6 newtons, plus the x component of the force F32, which is 0 because it's along the negative y direction. And so the total x component is 6 newtons. Similarly, we can get the total y component by adding the y components of the individual forces. And F31 has no y component, it's 0. And F32, the y component is negative 18 newtons, and so the total y component is negative 18 newtons. And so the force is equal to 6 newtons along the x direction minus 18 newtons along the y direction, where these x hat and y hat are unit vectors, which have just a magnitude of 1, and they're just used to illustrate the directions. Okay. Now we know the total vector. Its x component is 6. Its y component is negative 18 newtons. We can use Pythagorean's theorem, which says that we add the squares, the sums of the squares, and take the square root. And when we do that, we get that the magnitude of the force is 19 newtons. And we can use the tangent equation, right? Tangent is opposite over adjacent, which is the y component over the x component, and that's negative 18 newtons over negative 6 newtons. And when you hit inverse tangent, you get a negative angle, but it's 72 degrees. Negative means clockwise if we start along the positive x direction. Okay, so the force is 19 newtons, and it's pointing 72 degrees clockwise from the positive x direction. Okay. And we could do this if we have more than 2 charges acting on Q3. We just would calculate the magnitude and the direction of each force, add up all the vectors, and the magnitude and the direction give the total magnitude of the force and the direction of the force. Okay. So that's how to calculate the net force using superposition if we have more than one short charge. Let's go a little more here on this set of notes because we're almost done. And then in return, there will be one less lecture on Thursday. There won't be a lecture on Thursday. This will be today's lecture. Will go a little longer. Then we'll have tomorrow, and then we'll take off on Thursday because I made the first lecture a little long as well. So what we want to do here is we want to rank the magnitudes of the net forces here. So we have 3-point charges, and we have 3 different configurations. And for each configuration, there is 2 negative charges and a positive. And what we want to do is we want to calculate, or we want to determine under which condition the positive charge will experience the largest force. So in other words, for which configuration, A, B, or C, would the positive charge experience the strongest force? Okay. So what we can do here, we're going to do it mathematically, but let's just try to do it intuitively. And B is the easiest, so let's start with that one. Okay, here you have the positive charge in the middle, and it's repelled by it's attracted to both the charge on the left, the negative charge, so there will be a attractive force pointing toward the left due to the charge on the left. It's also attracted to the charge on the right because it's opposite signs. And so that the magnitude of that force is the same, but it's pointing to the right. So now we have 2 vectors pointing in opposite directions and they're equal magnitudes. So the net force on plus Q is 0. The force is balanced. The charge on the right exerts an equal attraction to the middle charge as does the charge on the left. So that one has 0 magnitude. Okay, so we know that B is going to be the smallest. Okay, now without doing the math yet, let's try to guess whether A will be bigger or whether C will be bigger. Okay, so let's look at A. Plus Q will experience an attractive force due to the middle charge. They're opposite signs, and they're separated by a distance d. The plus charge will also experience an attractive force due to this other negative charge, and the separation between that is d plus d, which is 2d. So it will experience 2 attractive forces, right, which will be pulling it to the right. Okay, one of them has a separation d, and one of them has a separation 2d. Now let's compare that with part C. Part C, this positive charge Q will experience an attractive charge due to the charge on the top, separated by a distance d. It'll also experience an attractive force due to the charge on the right. That also has a separation d, and they're both going to be pulling it toward, they're both going to be attractive. Okay? So my guess is that since the separation between the positive charge in either of these is the same distance d, and the separation over here on A between the first charge is d, but the separation between it and the second charge is 2d, that the attractive force in C is going to be larger than in A, because they're both separated by d, whereas over in A, the attractive force due to one of them, the separation is 2d. So let's solve it doing mathematically. So we can plug in magnitudes, and all of the magnitudes are Q here. So in part A, the total force is the attractive force. It's K times Q, and the separation between these two is d, so it's d squared, plus the magnitude of the force between the plus Q and the rightmost charge. So Q times Q, KQ squared, but the separation here is 2d, so it's 2d squared. And when you add all of these up, the magnitude of the force on the positive charge is 5/4 KQ squared over d squared. Okay. Now let's compare that with part C. So the charge Q experiences an attractive force, and the magnitude is K times Q, which is KQ squared over d squared. And that's a vector pointing upward because it's attracted. It will also experience an attractive force pointing to the right, and that's KQ squared again over d squared. And then remember, these are at right angles, so we need to get the magnitude of the total, we have to use Pythagorean's theorem. And we get that the net force is the square root of 2 KQ squared over d squared. And the square root of 2 is 1.41, and 5/4 is 1.25. And so we've proven that the force on the positive charge is larger in configuration C than it is on configuration A, and it's the smallest in B. Okay. So these are just a couple examples of how to calculate the total force on a charge due to 2 other charges, and we can expand this to many charges, in which case then you would perform an integral if it becomes continuous. We're not going to do that right now. We're not going to do that in the course, in fact, but you will probably do that in your more advanced courses, especially if you take electricity and magnetism. So that's the end of today's lecture. Here's your appendix on vector addition. So if you're a little rusty, go back and take a look at that. Again, we won't have a lecture on Thursday because we went over today and yesterday. So have a good day.